Today we're going to go over sections 5 and 6 of chapter 4, projectile motion. All right, so let's start with what projectile motion is. It's going to be a particle that moves in a vertical plane with only acceleration equal to the free fall acceleration g. So basically what that's saying is it's an object that's going to be falling or flying through the air, and the only force acting on it is going to be gravity, which is going to be pulling it down. G is going to be equal to 9.8 meters a second squared, as we've seen before. And it's always going to be facing in the downward y direction or in the negative y direction. Some examples are tennis balls, baseballs, footballs, lacrosse, racquetball, soccer, etc. Really anything that's going to be falling through the air. In projectile motion, the horizontal motion and the vertical motion are independent of each other. So that's the real key point here. The motions are going to be independent, which means we can have a set of equations for the x direction and a set of equations for the y direction, and they're going to act independently of each other. The only variable that's actually going to go between the two directly is going to be time, because the amount of time that a projectile is in the air does not change whether you're talking about the horizontal distance or the vertical distance. It's always going to land when it lands. Okay, so the initial velocity of a projectile can be written like this in our unit vector notation. You have some component of initial velocity in the x direction, some component of initial velocity in the y direction. Now, in this section, there's going to be a lot of notation and different ways of writing that notation. So I'll try to point out the commonalities between what we're writing. So the first thing that it shows you is our v naught x, or v0x, we say that is v naught x, is just the total initial velocity times the cosine of theta. So if I launched my projectile at that angle off of the x-axis, this is just going to be angle theta, the initial speed is going to be v naught. So this vector here, this hypotenuse, is going to be v naught, which has both x and y components to it. But if I just wanted the x component, I would multiply that by the cosine of theta, because if you kind of draw in a triangle here, so there's our triangle, there's theta. If I wanted just this component right here, just the x component, you would multiply by the cosine of theta. And the same for the y. So the y component is going to be multiplied by the sine of theta, right there. Right, so that's just what it's shown here. So v naught y can also be written as v naught times the sine of theta. Now the diagram here is showing the two different components and what they would look like. So if you're just thinking about the y direction, really the y direction is just going to look like a ball that's thrown straight up and comes right back down. So what the path would look like is it's going to go straight up and it's going to come right back down, and it's going to be accelerating the entire time because gravity is going to be pulling it down. Now the x is just going to look like a ball. It's going to look like a ball rolling across the table. So I'm just going to go straight across. It's going to have the same speed the entire time. There's no acceleration in the x direction. So v naught x is the same as vfx, which is the initial velocity, is the same as the final velocity, which is the same at any point in the path. There's no acceleration to it, so it's not going to change its speed. It's going to stay constant. So like I said, it's just going to be like a ball rolling across the table. Now, if you combine these two, you end up with this parabolic shape. So you have a constant x velocity, and you have a y velocity that's constantly changing. It's constantly accelerating, and that's due to gravity. So you end up with this parabolic shape. All right. I wanted to pause a second from the lecture and just mention the equations that we've had before in one-dimensional motion and show you what they would look like when we're talking about 2 dimensions. So far we've seen, we pretty much just used the x-coordinate for one-dimensional motion, so I'll list those again. So our x kinematic equations are going to be this. Notice how I'm putting an x subscript below everything. So I have the position x, the final position x, minus the initial position x, is equal to v naught x, which is our velocity in the x direction, times time, plus 1/2 the acceleration in the x direction times time squared. Okay, another equation is the final velocity in the x direction is equal to the initial velocity in the x plus the acceleration in the x times time. So this Vfx here is also usually written just as Vx. So if you just see Vx and V naught x, V naught is going to be the initial, Vx is just going to be the final velocity. But I like putting that f in there just to just so we're clear. And again, this is a subscript, so it's a small f. All right. We also have the final velocity in the x direction squared is the initial velocity in the x direction squared plus 2 times the acceleration in the x direction times our distance or our displacement, which is x minus x naught. Okay, and then the last one, x minus x naught, is equal to our velocity in the x direction, our initial velocity plus our final velocity divided by 2 times t. Okay, so we can do the same thing in the y direction. All right, so in the y, we have the same equations, but we're going to use y terms instead. So we have y as our displacement, y minus y naught, is equal to the initial velocity in the y times time, plus 1/2 at squared, which is acceleration in the y. And then the next equation again, I'm just rewriting all these equations and substituting in y where we had x. Okay. Now, something to point out, this term here, anytime we have the acceleration, sometimes it's written with a negative g in there instead for the acceleration. So we know that the acceleration in the y direction is negative 9.8 meters a second squared. So that term, sometimes you'll see as negative 1/2 g t squared, where g is just 9.8 meters a second squared. So notice how it's really the same thing, but we have the negative out in front instead of this positive here, and then g is just going to be 9.8 meters a second squared. So make sure you don't get confused on that. Just know that somewhere in there you're going to get a negative, whether you put it in the equation itself or you include it in the acceleration in the y direction. And that's also the same for this one and this one. Sometimes you'll get a negative g, or sometimes you'll just have the a in there. Okay. All right, so let's look at these equations a little bit further. So this is horizontal motion since there's no acceleration. So if we go back to our first equation here that we had in the x direction, in the x direction there's no acceleration. So you can just get rid of this second term. It just goes to 0. All right, so you're left with this equation here. Now, we mentioned earlier that v naught x could just be written as v naught times the cosine of theta, right? And that gets us the x component of our initial velocity. Now, looking on the y side, our acceleration is g. So again, we can put in that negative g instead of using the a. And that's what they did for this equation here. They also replaced v naught y with v naught sine theta. Okay. Another equation that we used is that final, remember I said sometimes they don't put in the f, so this is Vfy, or the final velocity in the y direction, is equal to the initial velocity in the y direction minus gt, or again, it could be plus at if a was negative 9.8 meters a second squared. So you get that negative sign in there somewhere. Okay, and then this other equation, again, they're just replacing our v naught y with v naught times the sine of theta. Okay, now if you take all these equations, you rearrange them, and you eliminate time, you can end up with this y displacement equation. equation. This is just another equation that you can use. You certainly don't need to. You can solve all the problems without bothering with this equation, but it is a straightforward equation if you're just trying to find the y displacement, you know the x displacement, you know theta, and you know the initial velocity with when it was launched. All right, so that's just an option for you. Okay. In the next section, we're going to talk about horizontal range. So when you have projectile motion like this, the horizontal range is this distance right here. It's the distance from the x distance from where you start to where you end. So our range is going to be, we're just kind of replacing this change in x with r from, let's go back to this equation right here. All right, so we just replaced delta x with r. And then we're going to use this other equation in the y direction. And then what it does is just combines these two. So you have r is equal to this term times both of your sines, or sine theta times cosine theta, and you end up with this result here. So really, the equation of importance here is what we call the range equation, and it's just going to be the initial velocity squared divided by g times the sine of 2 theta naught. So this is the initial velocity, not the components of initial velocity. It's just the full-on vector form of initial velocity. So you don't even need to worry about that. As long as we know what angle it was launched from and how fast it was launched, we can find how far it's going to go. All right, so the horizontal range R is maximum for a launch angle, oops, let's move this away, of 45 degrees. That's where half of the components are in the x direction, half is in the y, and you end up with a maximum R when you have an angle of 45 degrees. So that'll be important a little bit later on. All right, so let's go ahead and do an example problem. So in the figure shows a rescue plane flies at 198 kilometers an hour, which they go ahead and convert for you, 55 meters a second, and a constant height of 500 meters towards a point directly over the victim, where a rescue capsule is to land. So you have a victim over here in the water. We want to drop this rescue capsule to him. So what should the angle phi be of the pilot's line of sight to the victim when the capsule's release is made? All right, so phi is our angle here, which is a little bit of an odd angle. We don't usually do an angle that's off of the vertical axis, but that's pretty easy to deal with. So the plane drops the rescue capsule while moving at a constant velocity in level flight. While falling, the capsule remains under the plane because, again, the horizontal component is not going to change. So if the capsule and the plane are both moving at v naught, which is 55 meters a second, even if it drops the capsule, it's always going to stay right under the plane, right? Because the capsule is going to be moving horizontally at the same speed as the plane, even though it's going to be falling as well. All right, so once released, the capsule is a projectile. So its horizontal and vertical motions can be considered separately. Again, we want to break it into two different problems. So we don't need to consider the actual curved path of the projectile. We can just consider the line of sight shot. So we can actually just make a triangle. All right, so we see that phi is given by this equation. And this is just using, tangent is equal to opposite over hypotenuse. So the tangent of this angle is going to be the opposite, which is our x distance, or our horizontal range, and then our h component, which is the height. So ultimately, we want to use the equation to find x, right? Because we need to know x to find this angle. So we can use our x equation, which is given here. Now we know that x naught is just going to be 0, because if you start at the origin, that your starting point will be at 0. All right, so x naught is just going to go to 0. Because the capsule is released, not shot from the plane, its initial velocity, v naught, is going to be equal to the plane's velocity, which is what we mentioned. So we know also that the initial velocity has a magnitude of 55 meters a second and an angle theta naught is equal to 0, measured relative to the position, direction in the x-axis. but we don't know what the time is, and it turns out that we'll have to use the y components to actually find out what the time is. We have a little more information in the y side, so we can actually find the time there. So we're going to go ahead and use one of our kinematic equations, which is the first one. So y is equal to y naught plus v naught y, v naught y times time plus 1/2 at squared. And again, this plus 1/2 at squared could be minus 1/2 gt squared, just to make sure you get the negative sign in there. Well, y minus y naught is going to be 0, which is our final position. The final position in the y direction is going to be here at the origin, so that'll be 0. And our initial position is 500, so it's 0 minus 500 meters is equal to a negative 500 meters. This is important because this negative sign is going to probably have an effect on our equation and make everything work out. All right, so go back to this first equation. The initial velocity in the y direction, well, if we do, we know that our angle is 0. So v naught times the sine of 0, which gives us our y component, is going to be 0. So this term is just going to be 0. There's no y component of velocity right as it's dropped. It's going to start accelerating down, but it's going right with the plane before it's dropped, so it's not going to have any y component of velocity when it begins. All right, so that first term there is going to cancel out, and then all we're left with is y minus y naught, which is we found is negative 500, is equal to 1/2 at squared. And so we have negative 500 is equal to 1/2 times negative 9.8 times t squared. So now we want to solve for t. To do that, I'm just going to rearrange the equation, multiply both sides by 2, divide by negative 9.8, and then take the square root. So you get this plus or minus the square root of negative 500 times 2 divided by negative 9.8. And now here you can see why that negative sign was important, because if you didn't have the negative sign, you would get a negative inside the square root. And we know we can't do that. So we need these negatives to cancel out. When we do the square root, we're going to get plus or minus 10.1 seconds. Now we're going to choose the positive root here because we don't have it. There can't be a negative time. Time can't be negative. So we're just going to pick the positive one. Okay. All right. So now that we have this time, we can go back to our x equation up here, go and plug that time in and find what the x coordinate is. All right. So let me flip to the next page. So the equation we have is x minus x naught is equal to v naught x times t. Okay, so x minus 0, because our initial value of x was 0, is equal to 55 meters a second times the cosine of 0, which gets us the x component. Cosine of 0 is just 1, so it's just going to be the full value, times the time, which is 10.1 seconds. It's going to be x is equal to 555.5 meters. All right, now that we have x, we can go back to our tangent equation and find what phi is. So phi is going to be the tangent, or the inverse tangent, excuse me, of x over h. So phi is the inverse tangent of 555.5 divided by 500, and these are both meters. Oops. So that gets us 48.0 degrees. Okay. So this angle phi here is going to be 48.0 degrees. All right. Continuing on with that example. Part B says, as the capsule reaches the water, what is the velocity in unit vector notation and in magnitude angle notation? So what we're trying to find is this vector of velocity here. It has an x and a y component. It's going to be the angle of theta off of the x-axis. So the triangle that we can make is right here, this right triangle there. All right, so the horizontal and vertical components of the capsule's velocities, again, are independent, so we can work with them separately. We know that the x component of velocity doesn't change. There's no acceleration in the x direction, so it's just going to be the same. We can work that out mathematically by taking the initial velocity times the cosine of theta, but that's just going to be 55 meters a second. So we know that it's going to be 55 meters a second as the x component. Jumping over to the answer, writing it in unit vector notation, we just have 55.0 meters a second times I, so for the I direction. The component Vy changes from its initial value, V naught y is equal to V naught sine theta, because there's a vertical acceleration. Okay, so we can use, again, another kinematic equation to find what the final velocity is just in the y direction. And we're going to use this one here. So it's Vfy is equal to V naught, which is our initial velocity, times sine theta. So our initial velocity in the y direction plus a t. And again, they have it written as minus gt, same thing. All right, so this is going to be equal to our initial velocity times the sine of theta, which is going to be the sine of 0, so this whole term just goes to 0, minus 9.8 meters a second squared times the time, 10.1 seconds. So that's going to be equal to negative 99.0 meters a second. That's our velocity in the y, in the y direction. All right, and notice they put that here. You have a negative 99 meters a second with the j unit vector. Now, just to find the magnitude, you're gonna square both of these. So you have 55 squared plus 99 squared. And then take the square root of that. So you're just using the Pythagorean theorem. You're going to get 113 meters a second. To get the angle, you can just use cosine, tangent, or sine to get the angle. So real quickly, let's go ahead and do, let's see, 55 squared plus 99 squared, square root of that. It's going to get you 113 meters a second. If I wanted to do, well, let's use tangent. So theta is going to be the inverse tangent of opposite divided by adjacent. So the opposite is going to be your y component, which is 99, negative 99. And the x component is going to be 55. Okay, so you get a theta of negative 69 degrees. And we would expect that to be negative, because it's over here in the fourth quadrant. So if you're going down from the x-axis, you're going to be in the fourth quadrant. Okay, that's it for this lecture and for the rest of the chapter, actually.